So, like you said, I'm a current master's student, and so this is the preliminary results from my thesis study. I'm currently at 10 sampling events, and this will be the first 6 because I had to finish analyzing some stuff before I came. And so I'm looking at how precipitation patterns and potential climate change might affect sediment, nutrient, and biofilm dynamics in an acid mine drainage stream. And so for anybody who may not be super familiar with acid mine drainage, we work with it a lot at OU. And acid mine drainage is characterized by lots of heavy metals and really acidic water. And basically it forms when pyrite in an exposed coal seam or underground mine, usually pre-regulation mining, comes into contact with oxygen and water. It undergoes a series of reactions and ultimately forms iron hydroxide, sulfate, and acidic water. And then that acidic water can leach other heavy metals and other ions from the surrounding rocks. Here we have a lot of aluminum, but that varies depending on where you are. And so obviously that would be bad for aquatic life. And we see a lot of the direct toxic effects from heavy metals and from the acidity, and then the indirect toxic effects in the form of food web effects or habitat degradation when the iron hydroxides and sometimes aluminum hydroxides or other similar compounds form, and they start to coat the substrate, and then your algal communities, which is what biofilm is, if you didn't know, because I didn't know, and your macroinvertebrates can't attach to that substrate. It moves every time it rains, and so it's overall not great. We do treat acid mine drainage now, and we use both active and passive systems. The active systems are things like calcium oxide dosers or sulfidogenic bioreactors that involve a continuous input of material. Here we use a lot of the dosers, but they do allow the heavy metals and the hydroxides to form right inside of the stream. And so then you get a lot of that buildup that I was talking about. Passive systems circumvent that problem by directing the acid mine drainage through a natural or man-made ecosystem like a limestone channel or a series of wetlands before it discharges into the stream. But they're not suitable for every site because they're like gigantic for one thing, and then you have to have the right topography to install those. So like I mentioned, my research is looking at the potential effects of climate change. I'm hoping to look at both droughts and storms. For anybody who lives in this area, I don't have to tell you that it's been raining the entire summer, and I started in April. So I'm really just going to talk about storms today, but if you listen to me again in like a year somewhere, I might talk about droughts. So some research done by my advisor, Dr. Natalie Cruz at OU, has looked at how the underground mine acid mine drainage generation behavior might change during storms. And we basically have 3 major behaviors we see. Sparing occurs when your underground mine reaction site is cut off from oxygen during high flow, and so then you don't see any acid mine drainage being generated, and it's basically diluted in the stream. So if you look at your contaminant concentrations relative to discharge, discharge will increase more quickly than the contaminant concentrations. Flushing is the opposite, where you have basically a first flush of material from the underground mine or faster sulfide mineral oxidation, and you'll see your contaminant concentrations increase more quickly than discharge. And then what we've kind of termed normal behavior is just when they increase at the same rate. Of course, acid mine drainage streams are still streams, and so we do see the normal sediment scouring and the normal nutrient inputs from the surrounding watershed. And I've read a few papers recently who are looking at how storms can affect your total annual nutrient and sediment export loads, and they've found that a few really intense storms contribute a disproportionate amount of sediment and nutrient exports for the year for those watersheds. And so we're hoping to be able to look at least my sampling season and see if that's also true. So my research takes place here in Southeast Ohio in Hewett Fork. It's a sub-watershed of Raccoon Creek. We chose Hewett Fork because we have a lot of data for it, and it's treated, so we have a lot of different gradients and things that we can look at. So Hewett Fork receives acid mine drainage from the AS14 underground mine complex shown in that weird beige color. And it basically comes into the creek from 3 sources. There's 2 seeps that aren't shown on this map, Carbondale East and West seeps, and then the 2 tributaries shown and labeled Carbondale Creek and Trace Run are both acid mine drainage tributaries. And so the doser here is the Carbondale doser. It's a calcium oxide doser, and it's shown with a red star, and that was installed in 2004. They previously tried to use a wetland treatment system to treat it, but they couldn't reduce the metal and the acid load enough to restore Hewett Fork, so now we use the doser. But like I mentioned, dosers do create that kind of sacrifice zone, and so I'll be studying this gradient of water quality where your red zone is the impaired zone, and it's impaired from both the acid mine drainage and the alkalinity from the doser, and then you have the transition zone in green, and the blue zone is the improved zone. And the most downstream area near the confluence is actually currently meeting warm water habitat standards in terms of the macroinvertebrate community and the chemical water quality, but it's not listed as warm water habitat yet because the ongoing treatment required, it's like a gray area. And so because I'm looking at nutrients, we also want to understand the land use. Hewett Fork is largely within Zaleski State Forest and Waterloo Wildlife Area, but you do have some streamside agriculture, and 2 of my sites are in the middle of farms, and so that could have an effect. And so I'm testing several hypotheses. I'm going to ignore the droughts, like I mentioned, because it's not relevant anymore. But during storms, I'm expecting to see increased sediment transport in terms of total suspended solids. And I'm expecting to see the nutrient concentrations to be lower. And I had to think about why I thought that so many months ago. But I was expecting it to be exported and to be moving out of the system with the sediment. And I'm also expecting the biofilm abundance to be lower as they're scoured from the substrate, and the turbidity will prevent the colonies from growing. And I'm also going to be looking at water quality improvement, so trends as you move further away from the doser. And I'm expecting to see sediment transport decrease because you'll have less of those hydroxides forming and less of those in the system. And I'm expecting to see the biofilm abundance increase as they're able to adhere to some more substantial substrate instead of that fluffy stuff. As far as nutrients, I'm not expecting to see any trends with nutrients in terms of water quality because in acid mine drainage streams, particularly phosphorus, but your nutrients can be really attracted to the hydroxides forming, and they're basically like not in solution anymore. And so there's some evidence that acid mine drainage streams are like very phosphorus limited, but we'll talk about that because I'm measuring that. And so the goal of this project is to basically help inform practitioners of what to expect with ongoing climate change. I'm hoping that we can help prioritize projects and design efficient and cost-effective restoration relative to climate change, because right now we don't do anything with nutrients in acid mine drainage streams. They're like not a problem, but this might help provide more support for funding for like riparian enhancements and things like that. I'm also hoping to help provide more information about factors that might be limiting recovery in these streams where we see our chemical quality improved and our biological quality is still lacking. So I have 6 sampling sites left. One of them washed away. And so 137 is my reference site. It is still slightly impaired by acid mine drainage, but it's relatively better than the rest of them. And then I have 2 sites in the impaired zone, 095 and 090. And then 060 and 045 are in the transition zone, and 039 is my last remaining improved site. And also worth noting, 060 and 039 are both agricultural sites, but I'll probably say that again. So a trend, everything that I planned in this project, well, like most of it has gone wrong already. Which is fine. So this is my sampling schedule. It doesn't work out all the time, but using long-term climate data and some study done by Zeb Martin, who was a previous MSES student, we've defined storms and droughts relative to Hewett Fork. And so storm events are basically any rain event of 1 centimeter or more over a 3-day period, and that's just because that's when Hewett Fork shows a response. And I'll be sampling storm events 3 days after the rain event ends because it's very flashy and I have to be able to access the stream bed. Droughts, should we ever see one, are 7 days or longer without rain. And normal conditions are anything else, and those are sampled about weekly. I rely on volunteer assistance, so it kind of depends on when people say yes. But looking at this hydrograph, you can kind of see a big spike in discharge near the end of June, and that does affect my study because the doser was offline then. It ran out of material, but because the discharge was so high, you really don't see that blip in anything different in my study and in the macroinvertebrate sampling from this year. And so I measure sediment transport in 2 ways. I measure sediment deposition using these high-tech traps that I ordered from the Webster store. And they're basically just grids dug in to be flush with the stream bed. And when I go out, I pull out 3 containers from each site. I go back to the lab and I dry them and I weigh them and I average per site. And then on every 5th sampling event, I do a grain size analysis. And then I also do total suspended solids in triplicate at each site. I measure biofilm abundance using benthic chlorophyll A. So we basically sample a riffle if it's present. If it's not present, then we have a designated area of the stream that we take 10 rocks out of. And you use an O-ring to scrub a 25 square centimeter area of algae off of that into a composite sample for each site. They're frozen until I can analyze them in bulk, and then they're freeze-dried for 2 days and analyzed using a fluorometer. And then I measure nitrate and sulfate within 48 hours of collection using a hack colorimeter. And total reactive phosphorus, because iron interferes with phosphorus, those samples have to be frozen and analyzed in bulk using a spectrophotometer. I also compile my data with some other data. I use the USGS gauge station data from Boland's Mills in Raccoon Creek and weather data from the Scalia lab. And I do have long-term data from the Appalachian Watershed Research Group, but I won't be presenting on that today. And so what I do have is some time series analysis and comparisons of the parameters I've measured. So one of the things that went wrong is that the trap at 090 got buried, and I couldn't get it out for like a month. And so there's data missing in this. But what you can see is that you have higher sediment deposition in your impaired zone, which are the orange and the red sites. And what we think is causing that is, again, that iron hydroxide. And that's supported by a sediment chemistry study that my advisor, Dr. Cruz, did in 2013, where she studied a lot more sites than I'm using. And she did the sediment chemistry throughout Hewett Fork and found that that's where the iron concentrations peaked. We're at 095 and 090, and then it was still high at 060, which is the next downstream site. And we also see a lot of sediment deposition at 039, which is a very agricultural site. The flow is very low at that site, and so it's likely a lot of smaller materials dropping out. However, my grain size analysis does not show that. And so I'm not sure what the large particles coming out at 039 are yet, but this was only one replicate, so I'm hoping when I do more grain size, I'll be able to see if that was a fluke or something like that. We do see a lot of smaller particles at 095 and 060, and I think that that is, again, those iron hydroxides at that site. The flow is also very slow at 060, and so you would see those smaller particles dropping out as well. My total suspended solids results show watershed effects in that they increase a lot during storm events, which you expect to see with watershed inputs and scouring. I also have very high total suspended solids at 045, which is that light green site. And the reason for that is because it's at the bottom of very steep topography, and so you get a lot of material moving through that site sometimes. I don't know why it only showed up once, but and so sulfate is interesting because sulfate is a nutrient, but in acid mine drainage streams, it's present in such high quantities that we actually use it to trace how far the acid mine drainage is traveling and when you're getting inputs from that underground mine. It doesn't change form and treatment either, so it's really good for tracing that. And what you can see is that the sulfate concentrations decrease a lot during storm events, which means that the underground mine is undergoing sparing and it's not generating acid mine drainage that would flow further downstream. And so you can also see that the sulfate pretty much decreases with distance from the doser as well. Nitrate, on the other hand, does show some effects of runoff as you have those big spikes during storm events. And you expect to see the big spikes at 039 because, like I said, there's a farm literally right next to the stream. But the spikes at 095 and 090, those red and orange sites, are interesting because I don't know where they're coming from. I think it might be because the biological activity at those sites is less because of all the iron hydroxides and the lower quality water. And so I'm thinking that they're not being used up, but stay tuned for more information. And I mentioned about the phosphorus before, how it's basically unavailable in these streams. And all of my data, I didn't even separate it into storms and normal because it's all 0, which supports this idea that there's very little phosphorus in the stream. And we also have support from extracellular enzyme activity studies and biofilms that show that the algae will exhibit a lot more energy trying to acquire phosphorus relative to these other nutrients in the water. And so we're excited to be getting more support for this idea that they're very phosphorus limited. My chlorophyll A is a little bit more complicated than the rest of my parameters because you can't compare chlorophyll A from site to site because of differences in habitat availability and canopy cover that would affect your algal communities. So we have to look at relative chlorophyll A, so it's shown here as z-scores. And they don't really show any trends from site to site either in the time series graph. But you do see that your chlorophyll A is pretty much lower during storm events, with the caveat that that mid-June event where all of your chlorophyll A is negative in the normal section, that's that big spike in discharge. It's following that. And so it's likely that the stream just hasn't had time to recover from all that water moving through. And so I'll be continuing my field season until November 1st. It'll be a 5-month field season, and then we'll be statistically testing some of the trends and overlaying discharge with the parameters that we've measured to see how related those are, and maybe even looking at droughts. So I should be done in March. And I do want to acknowledge all of the people who have helped me because I ask them every single week to dedicate half of their days to me. But that is all I have, unless you want to see how many words I can fit on a slide.
I'm not familiar with the z-score in relation to chlorophyll A. Can you explain a little bit more detail about that?
So I use it as z-scores. So it's a z-score per site, and so it's just showing how the chlorophyll A differs at that site per each sampling event. And so it is divided by site. I know it doesn't really show that. But it's just a way of standardizing that data because I can't look, like I could look at one site over time, but I can't compare that to any other sites because of the differences in where they might be able to live. Thank you.